Welcome to AI Paper Podcasts, where we dive deep into the latest research so you can quickly grasp the most important ideas and insights.
Hey there.
So today, we're tackling something really exciting. It's this quest to build AI agents that learn about the world just by watching it.
Yeah, watching, predicting what happens next, and then, crucially, using that understanding to actually do things.
Exactly, like learning an internal world model, sort of how we do, right? Learning from Sense's video in this case.
Understanding dynamics, anticipating the future. It's a big goal.
And the paper we're digging into today, V-JEPA from Meta AI, seems like a pretty significant step towards that. It's a scalable, self-supervised video world model.
It really is. And I think the key thing, the really interesting part, is how VGPT learns. It's not trying to predict every single pixel, which is super noisy and hard.
Right.
Instead, it predicts representations of masked parts of a video, but within a learned abstract space.
Okay, so it's focusing on the more predictable structural stuff, ignoring the random noise.
Precisely. That makes it way more robust. And the two in V-JEPA is all about how they scaled this idea up massively.
And that scale leads to some pretty eye-catching results, yeah.
Definitely. State-of-the-art on video understanding, prediction tasks, but maybe the headline result is the zero-shot planning for actual robots?
Zero shot, meaning they train it, then put it on a robot it's never seen, doing tasks it wasn't specifically trained for?
Exactly that. And it uses a surprisingly small amount of actual robot interaction data compared to the huge amount of video it just watched.
Wow. Okay. And it's versatile too. I saw something about language models.
Yeah, the representations it learns are so good that if you connect them to a large language model, it hits state-of-the-art on video question answering too.
So it's not just about predicting or acting, it's building a genuinely general understanding.
That seems to be the idea.
Yep.
Learning from observation, then applying that knowledge broadly.
Okay, let's really get into this V-JEPA paper then. Our mission for this deep dive. Unpack the architecture, figure out the secret sauce for scaling it, and look at what these results, especially in robotics and understanding, might mean going forward.
Sounds good. Where should we start? Maybe the human analogy.
Yeah, let's do that. You mentioned how we learn like a baby watching the world.
Right. You know, dropping toys, pushing things, you're constantly building this internal sense of physics, cause and effect, mostly from just observing with a bit of poking and prodding.
And that lets us predict, plan actions. We want AI to do that.
But it's tough for AI. Traditional methods often need tons of very specific interaction data, like labeled examples of actions.
Or they try to predict everything at the pixel level, which, as you said, gets messy. All those unpredictable details.
Exactly. And that's where JEPA, the joint embedding predictive architecture, comes in as a different approach.
Okay, so break that down. What's the core principle?
The core idea is don't predict pixels. Instead, you take a video, mask out some parts of it, maybe in space or time, and the model's job is to predict the representation of those missing parts using the context from the parts it can see.
Representation. So like a compressed, abstract summary of what's in the missing part.
Yeah, exactly. And embedding in a learned space. It forces the model to capture the higher level meaning or structure, the dynamics, what's likely to be there, without getting bogged down in rendering every blade of grass perfectly.
That makes intuitive sense. Focus on the essence, not the surface details.
Precisely. It learns the predictable structure, ignores the irrelevant stuff, and the beauty is it can learn this just by watching videos. Self-supervised learning.
Meaning no human labels needed for the pre-training, just raw video.
Right. You can feed it massive amounts of internet video data. The prediction task itself provides the learning signal.
Okay, so V-JEPA established this core idea, but V-JEPA 2 took it to another level. You mentioned scaling. What were the key ingredients there?
They spell out four main things that really push the performance. First up, data scaling.
More video.
A lot more video. The original used about 2 million videos. V-JEPA trained on 22 million.
Oh, okay. More than a tenfold increase. Was it just any 22 million videos?
No, and that's important. They talk about curating the data. They used a cluster-based method on the huge YT1B dataset, but also mixed in specific datasets known for certain things.
Like
something V2 for motion understanding, kinetics for human actions, How-To 100M for instructional stuff, even ImageNet for still images.
So a curated diet of videos, not just random stuff.
Exactly. And they found this curated mix actually boosted performance noticeably by about 1.4 points on average across tasks compared to just using less curated data. Quality mattered.
Okay, so smart data scaling. What's number two?
Model scaling. Bigger network. They went from a Vision Transformer Large, or VITL, which is about 300 million parameters, to a VIT Giant, VITG, that's over 1 billion parameters.
Okay, so bigger brain, fed more high-quality data, standard deep learning scaling playbook, partly.
Pretty much. Bigger models can capture more complex patterns given enough data. Third ingredient.
Go on.
Longer training. They simply trained it for much longer. Original V-JEPA was 90,000 iterations. V-JEPA 2 went up to 252,000.
Nearly 3 times longer. How'd they manage that computationally?
Yeah.
And keep it stable?
They used a smart learning rate schedule, a warm-up phase, then a long phase where the learning rate stays constant, and finally a decay phase. This seems to help stabilize training for these long runs with massive models and datasets.
Right, makes sense. And the final scaling piece.
This one's quite clever, higher resolution and longer clips. Ideally, you want high-res, long videos for learning fine details and long-range dynamics.
But that's computationally brutal, right? Especially with a 1 billion parameter model.
Exactly. So they use progressive training. They start the training with lower resolution video and shorter clips.
Okay.
During the initial warm-up and the main constant learning rate phase. Then, only in the final decay phase, when the model's already learned a lot, they switch to the higher resolution and longer clips.
So you get the benefit of the rich data, but only towards the end, saving massive compute earlier on.
Precisely. They report it gives an 8.4x reduction in GPU time compared to training high-res from the start. It's a really efficient way to get those benefits.
Okay, so those 4 factors, curated data scale, model scale, longer training, and progressive resolution, are the keys to V-JEPA 2's powerful observational learning.
That seems to be the core recipe for the base model, yeah.
But like we said, just observing isn't enough for an agent. It needs to act. How do they connect this powerful observer to action?
Right, that's where V-JEPA 2 AC comes in. The AC is for action conditioned.
A separate model.
Yes. They take the big V-JEPA 2 encoder, the one trained on 22 million videos, and they freeze it. It acts as the fixed visual perception system.
Okay, so its understanding of the world is locked in.
Then they train a new, smaller model, a 300 million parameter transformer on top of this frozen encoder. This AC model learns to predict the future based on actions.
And this model, the AC part, how much robot interaction data did it need? Was this another massive data set?
And this is maybe the most exciting part, no. They trained VJ2 AC using just under 62 hours of interaction data.
62 hours, that sounds incredibly small for learning robot control.
It is, especially compared to methods that need thousands of hours. It was unlabeled teleoperation data from a Franca robot arm, part of the droid dataset.
So the heavy lifting of understanding visual dynamics comes from the massive observation pre-training.
Exactly. And then you only need a relatively small amount of interaction data to teach the model how its specific actions influence the world's state, as perceived by the powerful base encoder.
Wow. Okay, so what does VJT2AC actually learn to predict from that 62 hours? Still predicting representations.
Yes. It learns to predict the VJP2 representation of the next video frame, but now it's conditioned on the representation of the current state and the action the robot took.
So if I see this representation and I do action X, the world will look like this next representation.
That's the essence of it, learning action condition dynamics in that abstract, robust representation space.
And having that predictive model is the key to planning, right? How do they use it to actually control a robot?
They used a technique called Model Predictive Control, or MPC. It's pretty standard in robotics.
How does MPC work in this context?
Okay, so the robot has its current camera view and a goal image, like where it wants its hand to be, or what scene it wants to achieve. It uses the V-JEPA 2AC model to simulate what would happen if it took various sequences of actions. If I move left, then down, what will the world representation look like in 2 steps?
It's planning by imagining the future using the model.
Exactly. And it needs a way to score those imagined futures. How close do they get to the goal?
And how does it measure that closeness in representation space?
They calculate the L1 distance, basically, the sum of absolute differences between the predicted future state's representation and the goal image's representation run through the same V-JEPA 2 encoder.
So it wants to find actions that minimize that distance, that make the imagined future look like the goal, representationally speaking.
Precisely. It's minimizing a goal-conditioned energy function, where lower energy means closer to the goal representation.
And how does it search through all the possible action sequences to find the best one?
They use an optimization algorithm called the cross-entropy method, or CEM.
CEM.
Yeah, it's an iterative approach. It samples a bunch of random action sequences, uses the V-JEPA 2AC model to see how good they are, how low the L1 distance gets, keeps the best ones, and uses those to guide the sampling in the next iteration. It gradually focuses the search on promising action sequences.
Okay, so it simulates, scores, and optimizes to find the next best action. And the really cool test was deploying this zero shot.
Yes, this is critical. They took the model trained on that 62 hours of droid data from one lab setup and deployed it directly onto Franka robots in 2 different labs with different lighting, background setups the model had never encountered during training.
And just using a single RGB camera, no depth sensors or anything fancy?
Just one camera, standard monocular vision, a really challenging real-world test.
So the million-dollar question.
Yeah.
How did it perform? What could the robot actually do?
For relatively simple tasks, like just reaching a target location shown in a goal image, it did remarkably well. It consistently got the robot's end effector to within about 4 centimeters of the goal.
That's pretty accurate for zero-shot visual control.
Yeah, and they showed the error decreased smoothly over time, kind of like visual servoing, but learned entirely from the data, not programmed.
Impressive. Did they try more complex things, like actually manipulating objects?
They did. They tested grasping objects, reaching while holding an object, and even full pick-and-place sequences.
How did pick and place work? That involves multiple steps.
Good question. They guided it with a sequence of sub-goal images, like first show it a goal image for grasping the object, then once grasped, show it a goal image for reaching above the drop-off point, then a final goal image for placing it.
Breaking it down with intermediate visual goals. Makes sense. And how did this V-JEPA 2AC planning stack up against other approaches? They compared it to something called Cosmos.
Right. They compared it to a world model based on Cosmos, which tries to predict future video frames at the pixel level. And this is where the representation-based approach really showed its strength.
How so?
Efficiency, mainly. Planning the next action with V-JEPA 2AC took about 16 seconds on a high-end GPU. The Cosmos model, because it's generating full video frames, took around 4 minutes per action.
4 minutes? That's basically unusable for any kind of fluid interaction.
Pretty much. And V-JEPA 2AC wasn't just faster, it also achieved higher success rates on the manipulation tasks they tested compared to the Cosmos baseline.
So planning in the learned representation space seems much more practical and effective for control than planning via generating pixels.
That's the strong implication, yeah. It hits a better trade-off between predictive capability and computational cost for this kind of planning.
Okay, so the robotics results are really compelling. Zero-shot control from limited interaction, leveraging massive observation. But the power comes from those underlying representations learned by the base V-JEPA 2. Are they useful beyond just robot control?
Absolutely. They showed the frozen V-JEPA 2 encoder is a strong foundation for other standard video understanding tasks.
Like classification, telling what's happening in a video.
Exactly. They're just trained a simple linear classifier or an attentive probe on top of the frozen features, and it got state-of-the-art results on benchmarks that heavily rely on understanding motion, like the something V2 dataset.
What about tasks that are more about appearance than motion, like classifying objects in ImageNet, treated as single-frame videos?
It was competitive there too, and when they averaged performance across 6 different diverse video classification benchmarks, V-JEPA 2 achieved the best overall average score compared to other leading self-supervised methods evaluated the same way. And remember that progressive training with higher resolution, that helped boost performance across these classification tasks as well.
So, strong general video understanding capabilities. What about prediction? Can it anticipate what's going to happen next, say, with human actions?
They tested that on the Epic Kitchen's 100 benchmark, which involves predicting future actions in cooking videos. Performance scaled well with the model size, as you might expect. But here's another really surprising result. V-JEPA 2, which remember was pre-trained without any language data at all.
Right, pure video.
It actually outperformed previous state-of-the-art models on this action anticipation task. And that includes models that explicitly used powerful large language models to help with the prediction.
Wait, really? The vision-only model beat vision plus language models at predicting human actions. How is that possible?
It's counterintuitive, isn't it? The paper suggests that perhaps the very strong spatiotemporal representations learned by V-JEPA capture the subtle visual cues that precede actions so well that for this specific task and benchmark, it outweighs the benefit of the explicit language reasoning in the other models.
That's fascinating. It implies a huge amount of predictive signal is purely in the visual dynamics if you can learn to capture them properly.
It seems so. They showed some visualizations of plausible predictions, like anticipating someone would put down an object or close a drawer, though they also noted limitations and failure cases, as you'd expect.
Sure, anticipation is hard. Okay, and one more area connecting these visual representations to language models for question answering.
Yeah, they wanted to show the versatility of the V-JEPA features even further. So they used it as the visual backbone for a multimodal large language model, or MLLM.
And the novel angle here was?
Using a visual encoder, V-JEPA, that had zero exposure to language during its main pre-training phase. Usually MLLMs use visual encoders that have already been trained with some form of image-text data, like CLIP.
Right, so how do you bridge that gap? How do you get a language model to understand the outputs of a language-free visual model?
They used a technique called visual instruction tuning, building on frameworks like Elava. Basically, you train a small connector network, a projection layer, that learns to map the V-JEPA output embeddings into a format that the LLM, they use Llama 3.1, can understand.
And you train this connector
Using large data sets of paired video image and text descriptions, they scaled this alignment training up significantly, using up to 88.5 million image or video text examples in their biggest experiments.
So a separate alignment phase teaches the LLM how to interpret the V-JEPA features. How did that perform?
Pretty well. In controlled comparisons, V-JEPA was already competitive with vision encoders that had seen language during pre-training. But when they really scaled up that visual language alignment data, the MLM using V-JEPA achieved state-of-the-art results on several video question answering benchmarks, demonstrating it could effectively ground language in the V-JEPA representations for complex reasoning about video content.
Okay, let's try and wrap this up. If you had to summarize the big picture significance of V-JEPA, what would it be?
I think it provides really strong evidence for a particular path towards more general AI agents, specifically the path of learning a really comprehensive world model, mostly from passive observation, just watching tons of video, and then fine-tuning or conditioning that model with a much smaller amount of actual interaction data to enable specific actions or tasks.
And the key seems to be learning those dynamics in the latent representation space, the GBAC approach, rather than getting stuck on pixels.
Exactly. That seems particularly crucial for making planning computationally feasible and robust, as we saw with the robotics results.
It feels like a validation of leveraging the massive amounts of unlabeled video out there. That observational data is incredibly rich, and this approach taps into it effectively.
Yeah, and combining that vast observation data with targeted but limited interaction data seems like a very promising way to scale up capabilities in areas like robotics, which have always struggled with the bottleneck of interaction data collection.
So V-JEPA demonstrates a unified approach, one core visual understanding model that excels at observation, prediction, and enables zero-shot planning and action.
It really does. It ties together perception and action through this learned world model in a very compelling way, delivering top results across a surprisingly wide range of benchmarks.
A really significant paper then, pushing self-supervised learning from video and showing its potential for embodied AI.
Definitely one to pay attention to.
Which brings us to our final thought for you, the listener, to ponder. If models like V-JEPA can build such capable world models, allowing things like zero-shot robot control primarily just by watching the world, with only a little bit of interaction needed to connect actions. What does that imply about the fundamental limits here? How much can an agent learn from passive observation alone? And how much active interaction, how much trial and error is truly necessary to build general embodied intelligence?
Yeah, it's a fascinating question about the balance between observation and interaction and learning, something to think about.